Okay folks, so what we're going to do now is I'm going to be introducing you to the tools that we're going to be using in class for synthesizing and building our designs. This is where we'll be coding, testing, building, and so I think it's important for us to take a real close look at the tool itself and how it works and what are the different phases and pieces of the design in here. So we're going to start by looking over on the left hand side. You'll notice that there's this project manager tab in the left hand area where I've got my mouse. And if you click on that, you'll notice that it can expand or collapse this project manager tab or selector. Over here in the middle, we have the project manager window, and this is an important window, and it's going to be one that we use a lot during our simulation and testing. The most important one right now is the sources window, which I'm highlighting here. The sources window is where all the sources for your design come into play. This is where your design file is. This is where your test bench file is going to reside. And it's also where your constraint files are going to be. Now, a constraint file we haven't talked about yet, but a constraint file is basically a file that tells you how to connect your inputs and outputs to specific pins on the chip that you are targeting. So the way the system works is when you start and build your first project, you are going to be specifying the exact chip or board that you're targeting. And in our case, we're going to be using the Basis 3 board as our example. And that particular chip has been already put in place in here so I can show you this example. We'll go through some examples later where we go through the process of starting up a brand new project. But right now, for the introduction, we just want to see kind of how the different pieces work so you don't get scared by the complexity of the display. So the sources here are divided into three pieces. We have our design sources. The design sources have all of your VHDL files that are used in the design, the components that you're building. And in our case, this is just a single component, just the intro starting component. The next tab, or the next selection, is the constraints file. Now the constraints file tells us how to hook up the various pins to specific pins on the exact chip that we're targeting. Now remember, we're trying to build a design that we can synthesize into actual hardware, which means we're going to be targeting an actual chip, and we're going to want to tell it where exactly to hook up to that chip, what pins to hook up to. Then we have our simulation sources, and this is where you put your test bench file. And the test bench file is the file that you would use to include your design in so that you can apply test signals to it to see if it works. And we're going to go through that process real quick here. Now we'll start first off by double-clicking on the intro. So intro is the file. This is part of our intro data flow architecture. So if I click on this, you'll see that the code comes up that we had been using previously in our discussion, and it's all together. So everything's been combined in one now. So it's all together in one place. You'll notice that I've added a comment header, which is incredibly important because comment headers are something that are critical for you to tell other people what your design does. This is basically your way of saying, here's what my component does and here's how you should use it. Don't leave off the comment header. I frown very severely on that. That's a big part of a good design, is documenting your design so others can actually use it. Now, this is a very simple design, so it doesn't require a super complex description, but every file should have a description header at the top, no matter what. The first two lines are also relatively new, and these basically define the library of definitions that we will be using for our design. Since we're using the standard logic reference as far as signal types, we have to include the standard logic 1164 library. And so that will probably appear, no, that will definitely appear at the top of every single one of your design files. So that's just something that you'll see always at the top of your design files. As we scroll down, you can see the entity description here that we put in to define the inputs and outputs for this particular system. And then the simple architecture description that we talked about earlier, and that's also appeared in here. So this is a fairly simple file for a fairly complex combinational logic design, just using 3 Boolean equations to define what it is we want it to do. So that's not too bad. So let's take a look at our test bench. Now the test bench we talked about earlier, we're going to click down here to the simulation thing here, and we're going to double click on that and pull up the intro test bench file. And this again has a nice little comment header that tells you what goes on inside this file. And it also has a couple of features of a general test bench that we will talk about in great detail later, but I just want to briefly introduce. You'll notice that the entity of a test bench is completely empty. That means the test bench doesn't have inputs or outputs. It's a self-contained component, and everything happens inside. And we use software to analyze the signals that are generated inside the component. The architecture description has also done something that is probably relatively new to you, is the definition of a constant. Now, you should never hard code values in your design. You should never hard code a value for anything. It should always be in a constant at the top of the page so that you can change it or modify it. Even things as simple as checking for a high or a low should be done through constants. I always set a constant to indicate active state, and most of the designs that you'll see that we create will have an active state of high, and so that's what we're doing up here at the top. Then we declare the unit under test. Now this is, again, I'm introducing some complexity here on our intro, but I just want you to see the bare bones basics of what's going on. This is the unit under test, or the intro component we are testing. So remember, in a test bench, what's happening is we're creating a component and then taking our component that we want to test and we're sticking it inside that component. And then we're going to be applying signals to the inputs and then looking at what the outputs are doing. And so anytime you do that in a test bench, you have to create the you have to bring in the component as a component declaration, and that's what this is all about here. This part is the component declaration. For every component declaration, it's not required, but I think it's an important thing to do. We want to basically declare signals of the same exact name as the port pins in their unit under test. This means that you're less likely to have issues later on when you're debugging to figure out what the signals are. So I wouldn't use two separate types of names. I would use the exact same names, because remember, the signals are inside the test bench component, not inside your intro component. Those are defined internally inside the intro component. Then all we have to do at this point is come down here and see that the unit under test, which is the device that we're dropping in, our intro component, is going to be plopped down inside this test bench. That's the device that we're testing. And then we're going to use a thing called a process to drive the signals for us. Now, we're going to talk in great detail about what a process is and how a process actually works. But for now, just recognize that this basically represents a switch driver block in our test bench block diagram. Then it outputs signals on SW1, 2, and 3 so that we can drive them with different values and see what our component does. Is it going to behave properly? So what we're doing here is we're simply going to drive it with the 8 possible values that you can apply for 3 switches. We'll start off by driving the switches here with a low signal. Okay, so they're all low, non-active signals. And then we're going to wait for a little bit after we've done this before applying the next signals. And this gives us time in our simulation to see the waveform over a period of time. So if we wait for 100 nanoseconds, that means that all the signals will start out low and they'll stay low for 100 nanoseconds. Then they'll change once we go past that wait time. And we change them now to where switch 1 is only active and the rest of them are off. We do this repeatedly 8 times so that we can test, we've got 3 bits, so it's 8 possibilities. You've got 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. All of those are what we're going through by hand by doing this. And then the very last thing we do in our test bench is we activate a wait statement. Now, the wait statement basically freezes the process in place and doesn't go any further in the simulation. And we're going to talk more about what all that means as far as how a process works and how it processes information. But for now, this is what we'll stick with as far as our just brief demo. The last and final piece of the puzzle is our configuration file. And that's this Basis 3 master file. You can download this directly from Digilant, and they have it on their website. It basically maps out all the pins on their board to the devices they're attached to. So all the switches, LEDs, everything is in that file and defined as to which pins they go to. Let's open it up by double clicking it so you can see what it looks like. It's not a mystery, it's just a text file. So there's no magic involved here. This is simply a design that allows you to go through and set how each pin is connected to each device. So let's take a look at the first two lines here. Now notice that there's hashtags in front of all the lines. That's a comment delimiter inside the configuration file, not in a VHDL file, in a configuration file. It's unfortunate that they have a different format for the configuration file for commenting, but that's the way it's done. So in the formatting file, a pound or a hashtag sign is used to indicate a comment. So anything that has one of those in it, everything following the hashtag is comment, so it's ignored by the system. You'll notice that there's only a handful of lines that are active, and the most important here is these two right here are for switch number 1. Okay, so now this basically activates switch 1 and makes switch 1 part of the design. So you remember in our entity for our component, we were connecting switch 1 to something on our board. So this is basically saying I want to connect the signal switch 1 to a physical board switch, and in this particular case it's at pin V17, and that's what the package pin designation means. So you're setting the package pin property for V17 to switch 1. You're also telling it that this is the IO type. This is basically a low voltage CMOS 3.3 volt pin, and that's what the next line does. So there's two lines that are defining the interface to that one pin. There's lots of other things that you can do, but we don't need to do, not for this design at all. This one defines switch 2, and this one defines switch 3. If you scroll through this file, you'll see that every single resource on the board is represented and commented out, okay, except for the ones that we're going to be using. The next ones that we're using is the LEDs, and this is LEDs 1, 2, and 3. Notice the name is in the design here. You say port, and then LED 1 is represented here, LED 2 is represented here, and LED 3 is represented here. So this is basically a file that says, all right, hook this signal name to that pin, this signal name to that pin, this signal name to that pin. It's been defined by Digilant because they made the hardware. They know which pins are connected to which devices, right? And so you don't have to worry about that at all. You just come in here and you uncomment the lines that you want to use for your design, and you're done. You do have to import it as part of the constraints of the design, but that's relatively easy, and we'll see that in our next example when we go to a little more sophisticated design. All right, so that's the main pieces. Let's go to the process of actually simulating the design. Now, to simulate the design, that means you're going to be running the design against the test bench. We had our test bench file over here, and the test bench file was applying dummy signals, or real signals, but in software, to our design to see if it works. And so to make that work, you would run over here to the simulation tab, and you would click run simulation. Now, I've already run a simulation. I've got it started. This is a behavioral simulation. And so in a behavioral simulation, what we're basically doing is we're pulling up all the signals and running it for a certain period of time. Over on the left-hand side, you'll see that we see a waveform that represents the signals we put in, and then the signals that are coming out. So you can move your mouse and click on every part of this design, and you can look over here in the value column and see what values are going in. If we click here, we notice that all inputs are 0, which means all LEDs should be 0. This last one, this active, doesn't really need to be there. Let's see if we can get rid of that one. We don't need it. We're not deleting it from our design. We're deleting it from our waveform diagram because it's just not, it's clutter. And basically, if we click over here, we see that we've got switch 1 active, but switch 2 and 3 are not, which means it's only one LED active. let's just grab a value somewhere down in here. How about this one? We have 0, 0, 1, which means also 1 active. And if we go here, we have 1, 0, 1, okay? And so we have 1, 0, 1 at that time, and that's 2 LEDs that are active. So everything seems to be working just fine. And if we go out here where all 3 are active, that means all 3 of the LEDs are turned on. So based on looking at the waveforms, it appears that our design is working the way we expect it to and the way we want it to. All right, so that's good news. Well, let's take a look then at the next steps. Once we've simulated our design and we feel fairly confident that it's running, we can basically go down to the process of doing a synthesis. Now, synthesis is the process of carrying your written design and translating it into hardware. Okay, so it's a 2-step process. We're going to talk in great detail later about what those steps mean, but the first step is called synthesis, which basically takes your design and breaks it down into fundamentally mapping it to components that are part of this particular FPGA we're targeting, right? So it carries it the first step. The second process is called implementation, and the implementation phase. So if I do this, I click on synthesis and I say run synthesis, it will run the synthesis and it will generate the proper files that it needs. Once it's done, it will ask you, do you want to do an implementation? And so you'll do an implementation. Now the implementation takes that and goes another step and maps it physically to the actual hardware that's in that particular chip. So the first synthesis is really mapping it to resources that are part of this FPGA architecture. The second, or implementation phase, is actually mapping it to specific places in the chip and routing that chip. It's called mapping, and it's mapping the whole design to the chip. That's where a lot of the work happens. So the implementation part, once that's done, you're going to want to program the file. So what you would do at that point is you would go in and you would generate a bit stream. So you'll see down here in the program and debug, you have the ability to go down here and click on generate bit stream, okay? Now, when you do the generating bit stream, it'll go through the process. You'll see up here where my cursor is, I just started off the process of generating the bit stream. It's working and grinding to generate a file that has 1s and 0s in it, designed to program the FPGA to do what it is that we're asking it to do, right? So that's the gist of that. Now, once that's finished, it's going to pull up the hardware manager window here. Now we're going to let it grind away, but I already did this. So the hardware manager is still up from the previous run. And when the hardware manager comes up, it will have a button here to say, hang on, let me close this. In fact, let's close it and we'll let it finish the bit stream and we'll go through that process so you can see, because it is a multi-step process. I didn't want to go through this in the video too much because it does take a lot of time to go through a synthesis and implementation. We could do the magic of video by just skipping ahead and doing that, but sometimes I think it's better to watch things as they happen in real time rather than magically you fast forward to the next phase. So right there it's finished. So it finished with the generating the bit stream. So now you'll notice that a window pops up here, and it will probably come up with a default of open implementation. You don't want that right now. You want to open hardware manager. So you're going to open the hardware manager at this point. And when you click on open hardware manager, it basically just adds this little window up here at the top. And at the very top, you'll say open target. And that's where you're basically all you're trying to do is connect up to this device on the board and then get attached to it. Now, you can't do any of this until you've hooked up the board to the computer. So that should have been done prior to doing the hardware manager, right? So prior to starting the hardware manager, you're going to want to plug your board in and make sure that it's synced up with the system. And once that's done, you hit open target, auto connect, and it will find the device, and there it is. It's found our Digilent device. And then it comes up with a second line that allows you to actually physically program the device. So you can click on that, and you'll see that it's going to take the bit file that it generated here, and it's going to allow us to program the device by clicking on program. Boom. It's that fast. It's a very short design, but most programming does happen very quickly. So it's already programmed and ready to go. So let's take a look at the hardware. Okay, so here we are with our board. We've programmed the board with the code we just wrote, and let's see if it works properly. The way it's been configured is the switches down here, these 3 switches, are the SW1, 2, and 3. And then these LEDs are 1, 2, and 3. So if I push them up 1, that should be 1 on. Good. Let's try the other one. Yep, that's 1. And this one? Yep, that's just 1 that lights up. So now if we do 2 at a time, so if we do these 2, that's 2. But it would also work if I do these 2, and it would also work if I do the outer 2 as well. That's really cool. And then what if I push them all 3 up? There they are, all 3 are lit. So functionally, we verified it with our test bench, and then we ported it to hardware, and we verified it with hardware. So that's basically the intro example. Hope this was helpful in getting you started in the VHDL world, and we'll see you in the next video.